Okay, neural networks. Just give me 10 minutes and I will clearly explain how these work. No significant ML background required. And after you're done watching the video, there's a quick multiple choice quiz you can take in the description. Okay, let's say our goal is to predict how tall someone's going to be, so their final height once they're done growing. And we're going to use 3 pieces of information. Their parents' heights, so maybe like the average of their parents' heights, and then that's going to be one of our input variables. Their current height, so whatever height this person currently is, and their current weight. So those input attributes, as they're called, are essentially our inputs in that first layer or first column in the neural network. And let's say x1 is like the average of your parent's height, x2 is your current height, and x3 is your current weight. So think of x1, x2, and x3 as literally being stored in those nodes. But what are all these edges, right? What are all these edges over here? And what are each of these hidden nodes in the next column doing? So to understand that, we need to quickly review linear regression, and we'll explain it in a pretty straightforward way. It's a concept from statistics that's used to build models that can make predictions. For our case here, where we have 3 input attributes, the formula for linear regression would be something like y equals w1 times x1 plus w2 times x2, and then a similar term for x3 plus some constant number b. And x1, x2, and x3 are our input attributes, and if y is our model's prediction, our output for however tall someone will be, based on x1, based on x2, and based on x3, then it makes sense that w1, w2, and w3 factor in how important each respective input attribute is. The higher w1 is in this formula, the more important x1 is, which actually, if you remember, is the average of our parent's height. That reflects how important that attribute is in influencing what y would be. But what about b, which stands for bias? This is analogous to the b in y equals mx plus b. It's kind of like a base height that we would always add on, since no one would ever have a height of 0. So if we think of this as a model to predict how tall someone will be, linear regression is actually the simplest machine learning model. It's the foundation for the rest of AI. We would actually start off this model with completely random weights. So w1, w2, w3, and b would be initially random, and then over some process called training. I know it can be really annoying when people refer to training a model and they're not really clear as to what this means, but just for now, let's treat training as a black box, and later on we'll clear up as to what it is. But at a high level, the process of training is simply adjusting or tweaking w1, w2, w3, and b until they're the right values, such that our model's predictions, the model's prediction is y. We want y to be as close to the true answer as possible, right? So we want our model's accuracy for predicting how tall someone will be to be as high as possible. Okay, we're finally ready to relate it back to the neural network and our hidden nodes over here. So it turns out that each of these nodes, this node over here, as well as the 3 below it, are each performing linear regression. Each of these nodes are actually calculating some output y based on the x1, x2, and x3 that come in the previous layer. So each of these nodes independently is actually learning a w1, a w2, a w3, and a b. But at this point in the model, before we even consider what this output layer is doing, for some given person we passed into this network, right? We passed in their input features, their input attributes, their x1, x2, and x3, though those pieces of information about them that ultimately will affect how tall they will grow. At this point in the network, in our hidden layer, remember we're going through the network from left to right, and in our hidden layer, we have 4 numbers for that person, y1 through y4. But we want to predict one final number, right? That is going to be the model's prediction for how tall someone is. So our next layer actually has less nodes. We only have 2 nodes, and we can think of the number that is ultimately calculated in that node to be O1 and O2 for output 1 and output 2. Just as in the previous layer, O1 is calculated using our linear regression formula, except this time it has to factor in y1 all the way through y4. So we have an additional w4. We don't just have w1 through w3, we also have w4, and of course we have our constant term b. O2 is calculated the same way using y1 through y4, but we should remember that W1 through W4, as well as B for O2 for that node, are learned completely separately. So these two nodes are operating completely independently. If the point of this neural network is to predict how tall someone's going to be, then we wanted just one output number. So we might do something like this. We average O1 and O2, and that output is the model's prediction. So then the process of training this neural network to increase its accuracy based on some training data set where we may have a bunch of people and we have their input information. For every person in this data set, we have what their X1, X2, and X3 are, and we know what their ultimate height ended up being. This is the data set that the model would learn from. The process of training then is just the model figuring out what W1, W2, W3, and B should be for this node, as well as the three nodes below it, and figuring out what W1 all the way through W4, as well as B should be for O1 and O2 for those nodes. The ultimate goal of training, and we're just treating training as a black box for now, but the ultimate goal is to increase the model's accuracy on that training data set, and hopefully the model gives pretty good predictions later on for people it's never seen before when we pass in their input information. So that's the general idea of neural networks, but there's still a few things left to talk about. There is something called a nonlinearity. A nonlinearity function, such as the sigmoid function. These are essential for neural networks to perform better than other AI models, so definitely leave a comment if you'd be interested in a video on nonlinearities. And then training, right? We don't want to just treat training as a black box. What's actually happening there? It turns out that there is a simple formula, just a math formula, that explains how AI models are trained. And this is called gradient descent. And here's the formula. It's that the new weight, right? So we had those W1s, W2s, even the Bs. This formula applies for any one of those parameters of the model, as they're called. The new weight is equal to the old weight minus some number called alpha, which might be like 0.01 or 0.001, times a derivative from calculus, actually. And then this formula is basically applied iteratively over and over again inside a for loop until we have the right values for all our W's and B's so that the model's accuracy is strong enough. And I've got a 5-minute video going into more detail about this formula. That video is linked in the description. Lastly, you might be wondering how to implement this concept, right? How would you code this up in some sort of language like Python, which is typically used for ML? If you're interested in a video where I code up neural networks from scratch, definitely leave a comment as well. If you like my style of teaching, be sure to subscribe, and I'll see you soon.